For today's problem, we'll be going over how to figure out the density of a log. For the context of this problem, this log is in static equilibrium, meaning that as it's floating on the water isn't moving and the log is not moving. With this, that means pretty much all exterior forces acting on this log in the water are canceling out, except for two forces, specifically the gravitational force on our water and the gravitational force on our log. Now, both are exerted with the same gravity, therefore, mass times gravitational acceleration for each, the gravitational accelerations will cancel out for both, which leaves us with this expression. The mass of the log is equal to the mass of the water. Now, from here, we can actually get to the density. However, it's going to be a little bit stranger than you think because density is represented as mass over volume. However, volume isn't the exact thing that's going to get us to where we need to be. It's actually going to be the cross-sectional area. So allow me to write this out so I can explain a little further. Now, the density of our log times pi r squared, which is a circle, is equal to the density of the water times A. Now, A represents the cross-sectional area that the water is present on in our circle. Now, you'll notice that I have this kind of dashed line here and here. These are just the same circle, just drawn a bit more up front. Now, my variables are a little confusing here. Hopefully that's a little better. We have r as our radius, and h is this height where the water does not reach. So this entire bottom portion here is what we want for this a value. However, there is no just equation to find that, so we'd have to make our own. So that means that this minus this top hemisphere is what we want. So let's just write some general equations here to keep us on track. So pi r squared, the circle, what we want, minus that top hemisphere, which I'm going to represent as a naught. So how do we get a naught? So I've written this kind of cone, or a slice of pie, is how I was taught it as. This is a slice from our circle right here, if you let me draw it out. Just completing that figure there, this little portion up here is this little diagram. So we again have the radius on either side here, this little height difference, and from there we can make the generalization that to get a naught you need this. So I've reduced this to a lowercase a minus a naught. So we're going to refer to this cone or slice of pie as a, and a naught is going to be anything that's not this hemisphere, so basically this lower triangle formation. So let's work with what we know. So to get a and a naught are obviously the basics of our foundation, this absolute lower part that we have to work up from. A can actually be easily represented as. So we're going to add some variables. At the bottom here we have theta, so there's two thetas, so this would be 2 theta. We have a value of r minus h, because this radius would extend all the way through and include h. So to get that lower kind of backbone, we get r minus h. And this distance up here that's created by each theta is x. So that whole distance across is 2x. So how do we get that whole cone or slice of pie? Well, it's actually quite easy. So a is equal to 2 theta over 2 pi times pi r squared. Now this can be simplified a bit, and I'll do that for you real quick. A is equal to theta r squared. But now the question comes in, what is theta? We can't just take the measurement of some fraction inside a log. And I'd say you're correct, 100% correct. So we can do a bit of trig here to figure out theta, specifically inverse cosine. So we get a is equal to the inverse cosine of r minus h over r, again, adjacent over hypotenuse times r squared. So now that we have a, we need to figure out what we're subtracting from it. And like I said earlier, it's this triangular segment, which is actually, again, really easy. So as a triangle, 1/2 base times height. The base is kind of inverted here. That's the 2x. The height is the r minus h. The 1/2 will cancel, and we will get x times r minus h. Pretty straightforward. The only thing now is to subtract. So let's subtract. I see the problem here. I'm getting ahead of myself. Instead of subtracting, we should figure out what this x is. Because much like theta, we don't know what this little line across is. So we should get this in terms of radius and height. So how do we do that? Well, again, this problem is almost all strictly geometry. So use Pythagorean's theorem. There we go. So I kind of just went ahead and did it. So this is your theorem you'd set up. And when you solve for x, you get the square root of 2rh minus h squared. So plugging that in here, as well as plugging everything in here respectively, we can get a naught represented as such. So there we have a naught. So now all that's left is plugging it into this equation as well, and then into the density equation. So let's continue and just plug this away until we get to the density equation. This is starting to get longer and longer. However, we have the density of our log pulled down times is equal to the density of our water multiplied by A naught. Or sorry, all of A. This is pi r squared is now here as well. So a few more things to clean up. The density of water. Obviously, this log is not going to be in terms of grams, so we're not doing 1 gram per milliliter for water. We're going to be doing 1,000 kilograms per cubic meter. So this is going to be a factor of 1,000 here. That's going to be multiplied throughout here. And this pi r squared has to be divided to the other side. So those last few touch-ups, and we will have the density of our log as a function. And there you have it. The density of your log relative to the radius and height difference of the water of the log.